Now is the time to talk about RF pulses. The first thing to know is about flip angle beta, which, together with where B1 lies, defines the names of the RF pulses. Mathematically, beta equals omega 1 times Tp or gamma B1 times Tp, where omega 1 is the angular frequency of M0 flipping. Tp is the pulsing time, often called the pulse width, typically in the order of microseconds. And B1 is the pulsing power such that omega 1 equals gamma B1 radian per second. Here we see something similar to the fundamental equation of NMR. But this time the subscript is 1 rather than 0. In fact, they are exactly the same, but applied to different fields only. Apparently, by controlling how long the pulse is applied, M0 can be flipped to any angles, and by selecting where the B1 lies, M0 can be flipped to any direction in the Eulerian frame. Remember in the previous slide, we put B1 on the x-axis, which is called a 90-degree x-pulse. How about if we put B1 on the y-axis? The figures below depict what will happen. The first one shows M0 at equilibrium, where it aligns with B0. The second one shows M0 after a 90-degree y-pulse. And the third one shows the result of flipping M0 by a 180-degree y-pulse. To understand the values of TPs in the graphs, you can simply substitute them in the equation for beta above, which will then give the flip angles of M0. Try to apply the right-hand rule to the rotation of M0. You will understand how the rotation and the final position of M0 are defined. What will happen after pulsing? This is what we are going to explain with this slide, which is called nuclear spin relaxation. Apparently, as soon as B1 is turned off, the major magnetic field applied to the nuclei will then be B0. And of course, by the fundamental equation of NMR, all nuclei will then relax back to align with B0, i.e., back to their equilibrium state. In real time, the process can be depicted with a graph on the right, which is similar to a reverse process of the spiral motion we saw on slide 23. This process may last from a few milliseconds to a few seconds, depending on the molecular structure, the nuclear species, and the sample's physical appearance. For example, if it is solid or liquid. Remember that m0 is a macroscopic magnetic moment. In other words, it is a magnet. And now, during the relaxation, it becomes a spinning magnet that spins about B0. NMR signals can then be collected from a receiver coil surrounding the sample. This is similar to the spinning magnet inside an alternator of a generator or a car's engine, as shown below, in which there is a permanent magnet in the cavity of a coil surrounding it, where the coil is the brown wire in the graph. And the signals we collected contains the intensities and angular frequencies of all nuclei that were excited or resonated. However, nuclear spin relaxation is in fact not simply a reverse process of excitation. The end state, and hence the spin orientation of a nucleus, can be changed randomly due to molecular tumbling, collision, motion, and magnetic moment interactions. Therefore, a nucleus that was spin up before pulsing may not necessarily be again spin up in the end of relaxation. There are two kinds of relaxations. One of them is T1 relaxation, which is also called spin lattice relaxation or longitudinal relaxation. And the other one is T2 relaxation, called also spin-spin relaxation or transverse relaxation, which we are going to explain in the next few slides. What is T1 relaxation in NMR? In brief, T1 relaxation is a process for the Z component of all mu's to resume their maximum values at equilibrium. In this process, mz, the Z component of m0, recovers exponentially such that mzt is equal to m0 times bracket 1 minus e to the power of minus t over t1. It is a recovery process and is best depicted with the graphs on the right, where we can see clearly how mz recovers with time. You can see that about 90% of mz recovers in seconds, and then it takes much more time for it to fully recover. The second statement says that T1 and 1 over T1 characterize the exponential recovery time and recovery rate of mz respectively. Note that in the graphs, the T1 are 1.5 seconds and 3 seconds respectively. And obviously mz's haven't fully recovered at those times. If you replace the T in the equation with T1, then you can easily work out that at the time T1, mz is equal to m0 times bracket 1 minus e to the power of minus 1 because t is t1. And the value is 0.6321 m0. It means that only about 60% of mz has recovered at time t1. Apparently, t1 is not the time when mz has recovered fully, though it's called t1 relaxation time. That is why the word characterize is used in the statement. Let's have a look at the next three statements. The first statement says that T1 relaxation is a process towards the orderly state of thermal equilibrium, in which the magnitude of mz changes from 0 at the beginning to maximum in the end. The system changes from its higher energy state immediately after being excited towards its lower energy state after achieving equilibrium. The second statement says that it is affected by molecular tumbling and collision, and is related to dipole-dipole interactions. In other words, the nuclei physically contact each other in the process. The third statement says that energy or heat is released and transferred from nuclear spins to their surroundings, i.e., the lattice. This is a heat-releasing enthalpy process. What is T2 relaxation in NMR? In brief, T2 relaxation is a process in which the x and y components of M0, i.e., mx and my, or simply mxy, to exponentially decay towards the system's equilibrium, during which the opposite components of mx and my quickly cancel each other. Mathematically, as shown on the slide, mx and my equals m0 times an oscillating factor, either sine omega t or cosine omega t, and then times an exponentially decay factor, e to the power of minus t over t2. It is best depicted with the top two graphs on the right, where we can see clearly how the two m-axes diminish with time. Note that in the graphs, the T2 are 0.3 second and 0.8 second respectively. And obviously, both the m-axes haven't fully diminished at those times. If you replace the t in the equation with T2, then you can easily work out that at time T2, ms should be equal to m0 times cosine omega T2 times e to the power of minus 1, because t here has been replaced by T2. And the value is 0.3679 times m0 times cosine omega T2. It means that the signal's amplitude falls to approximately 37% at time T2. Apparently, T2 is not the time when mx and my have diminished fully, though it is called T2 relaxation time. That is why the word characterize is used in the second statement. The next statement says that T2 relaxation is a process towards disorderly state till the signal vanishes, and hence it is an entropy process. The total energy is unchanged in this process, though spin energy does transfer in spin-spin flip-flop interaction, in which a spin-up nucleus flips to spin down, while a spin-down nucleus simultaneously flops to spin up. There are two major factors involved in T2 relaxations. One of them is due to M0 relaxing back to equilibrium, because with the tipping angle of M0 getting smaller and smaller, MXY keeps decreasing. This can easily be understood because we have learned how M0 relaxes back to equilibrium on slide 25. Another one is due to nuclear spins fanning up with time, which will be explained in the next slide. Now, we'd like to talk a bit more about T2, because understanding T2 and how MXY diminishes is very important. And MXY is the only time domain NMR signal we can detect. Long T2 allows us to collect good signal with sharp peak in the spectra. And short T2 not only gives us very little chance to collect signal, but also results in broad peaks. They could be very broad and become unobservable. Why T2 relaxation is often so short? This slide explains a major reason. It is well known that T1 relaxation is usually in seconds, but T2 relaxation are often in milliseconds or even microseconds. It depends on the molecular structure, the nuclear species, and the physical status of the samples, because these are the factors that determine the amount of local magnetic fields. For example, macromolecules have many nuclei and many different local magnetic fields, and hence many resonance frequencies. It is the spread of NMR frequencies that causes MXY to quickly fan out on the XY plane with time, thereby cancelling the components in opposite direction, as shown in the figure below, where the fanning out vectors quickly fill the circle, and hence the opposite components are cancelled. When the circle is fully filled, all of the vectors are cancelled, and the signal disappears. Every T2 relates to the width at half of a peak height, usually measured in Hertz. The formula is given on the slide, i.e., T2 equals 1 over bracket 2 pi b, where the 2 pi is to convert the b from Hertz into radian, because the formula is derived with the angular frequency in radian, for which the proof will be given later. What are the relationships of T1 and T2 versus molecular correlation time and NMR frequency? which we have learned is directly proportional to the magnetic field strength B0. Here, the correlation time tau c is roughly equal to the time a molecule tumbling through 1 radian in solution. Apparently, large molecules tumble slowly, and hence their tau c's are longer. Small molecules, on the other hand, tumble faster. Again, this is best depicted by graphs. Note that log tau c equals -8 implies tau c equals 10 to the power of -8. And hence, the two graphs on the slide are equivalent, except that the top one was created by formula and the bottom one by experimental data. In both of the graphs, the right-hand side are for large molecules where tau c are larger. What conclusion can we get from the graphs? Let's focus on the top graph first, because it is less complicated, where the solid curves are for a stronger B0. We can see that the two V-Z curves on top are for T1s, and the two diagonally declined curves are for T2s. Here are the conclusions we can draw. Fact number 1. T1 is always greater than or equal to T2. Have a look at the graphs. On the left-hand side, the curves for T1 and T2 are overlapped, which means that for small molecules, such as water, their T2 can be as long as or very close to T1, regardless of the magnetic field strength B0. For large molecules, T2s are significantly shorter than T1s, and they are not significantly affected by B0. But T1s, the solid curves, on the other hand, are significantly longer in a stronger magnetic field. I'll let you digest the bottom graph at home, where the strength of B0 are in Tesla.